Hello everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. Uh, today, so today is the 10th lecture, right? Today is the 10th discussion session, and today we will be mostly solving some problems from the filtration and drainage properties of geosynthetics, and after that we will be having two more discussion sessions, the 11th and 12th. Next we will having on the 6th, that is the 11th. Then after that we will having on the on the 13th, and then on the 20th October we will be having the 13th discussion session. That will be around that will be just a wrap up session of 1 hour duration, and that's all. So just we have, after today's session we have two complete sessions left, and after that we will be having just one wrap up session. Okay, so our total three sessions are left after today's sessions, and with that we will be ending this course. And I hope that you are able to understand all the concepts very properly. uh, uh, Concepts very properly, uh, whatever is being taught to you. And if you have any doubt anytime, please feel free to write to me or contact the course instructor anytime, so that we can help you out. All right, so please study all the concepts properly and prepare well for your exams. Okay, because if you solve all the problems that are discussed in the class, in the discussion session, and then you also refer to the books and you solve some problems, that should be well enough, that should be good enough for the exam preparation. All right, and I'm hopeful that all of you will actually perform well in the exam, because a lot of problems were actually discussed during the discussion, during the interactive sessions, and also during the main classes, right? So let us start today's session. So what is filtration? Okay, so as I said, we'll be actually dealing into the two basic properties of geosynthetics that we already discussed previously also. So those two properties are filtration and drainage. So first we will be solving some problems from filtration, and after that we will be uh, solving for your drainage. Okay. Okay, so let us start slowly. So what is filtration? Filtration is that property where you allow the fluid to pass. You allow the fluid to pass, but you arrest the movement of the soil through it. All right, so you are allowing the liquid to pass, but you are preventing the soil grains to pass through it. Okay, so that is filtration. All right, so what, let us see what is written here. Equilibrium soil to geotextile system that allows for adequate liquid flow with limited soil loss across the plane of geotextile over a service lifetime compatible with application under consideration. So equilibrium soil to geotextile system. Okay, that means what? That means we will see that there is an equilibrium point. Okay, there is equilibrium point where the water that is coming out of the filter, that reaches the equilibrium state. Means there is neither loss of fines, neither less water that is going out. Okay, adequate amount of water is flowing out, so that equilibrium is reached. Okay, so equilibrium soil to geotextile system. So only if you place the geotextile, so along that geotextile or whatever geosynthetic we are placing for the filtration purpose, there along its surface we will be having some soil there, right? So that soil also needs to be graded in such a manner that it is actually compatible with the geotextile. Okay, there should be a compatibility between the soil and geotextile. So any geotextile you cannot place with any gradation of soil. If you place it like that without giving proper emphasis to the to each and every aspect, such as what is the gradation of soil particle that is there in that region, what will happen, that filter won't work properly. Either it will get clogged very easily, or either it won't uh, like function properly, or you understand, right? So it won't serve the purpose properly if you do not give proper attention to that. So you need to ensure that there is a compatibility between the filter that you are using and the soil that is there. Okay, so the system that allows for adequate liquid flow. So adequate liquid flow should be there, but there should be very minimal loss of soil particles through that filter. Okay, that is the main purpose. Okay, and this equilibrium, okay, adequate flow of liquid and limited soil passage should be maintained towards the complete complete service lifetime of that geosynthetic. Okay, complete service lifetime of that filter. Okay, complete service lifetime of that filter, that should be maintained. You should, your, as a designer, it is your target that whenever you design a filter, it should actually satisfy the, it should be running properly throughout its whole service lifetime. All right, one second, just give me a second. Okay, so yeah, so what are the functions of filter? Let us see. Retain particles of the base soil to be filtered. Yes, as I said, you need to retain the soil particles, right? Avoid piping. So what is piping? Piping means when loss of fine particles start to occur through a filter. What happens? Slowly the whole, look at, there is a pipe that is formed behind that soil, behind that filter, like slowly what happens, the soil keeps on, okay, so say uh, so here say you have a filter, okay, so as particles starts to come out of the filter, slowly a pipe like it's formed like this, okay, passing the soil keeps on getting passed out of the filter, and this piping phenomena is formed. Okay, then yeah, allow free flow of water. Yes, so obviously water should start flowing, or we should allow water to start flowing freely out of the filter. Okay, avoid external clogging. Yes, as I said, the soil particles should not clog the pores of the filter. Okay, avoid internal clogging. Survive construction environmental stresses, that you also should ensure. Then function capability as a natural irrigation. So these are the basic functions of the filter. Now this filter can be made up of, either you can use geosynthetic or you can use natural aggregates. So how you can use natural aggregates? Natural aggregates you can also own by proper use by properly grading. Say first to use like this, a little bit like the properly grading the amount of aggregates, you can make a filter with the help of aggregates. Okay, that is one. And the next what you can do, you can just use a geotextile. Okay, now these are the basic soil properties that you should know. Okay, so these we already discussed previously, right? This we already discussed previously. And so what are those properties? One is the D60 size, the D15 size, D85 size, D30 size, and D10 size. So what is this Cu? This Cu is nothing but the coefficient of uniformity. Coefficient of uniformity of any soil is that the D60 size divided by the D10 size. Okay, that is the Cu. And then you have the coefficient of curvature, Cc, that is nothing but D30 square by D10 into D60. Okay, that is the Cc, coefficient of curvature. And one more important thing, okay, that we will discuss. Okay, let us see, next we will discuss. Now the water flow from the base soil through the filter should not result in loss of fines from the soil. So we are emphasizing on this again and again. Okay, so there should not be loss of fines from the soil. Okay, or if any fines soil path, they should not clog the filter. So two conditions you have to ensure. One is that lot of fine particles should not pass through the filter. That is one. And second is, if any fine particle enters the filter, it should not clog the pores of the filter. Either it should go out or it should not even enter. Okay, that is these are the two criteria. Now these two criteria actually give the those we can actually represent in terms of some quantitative numbers, and those criteria are called the retention criteria and the permeability criteria. Retention means what? You have to retain the soil, you do not allow the soil and to pass through it. And the permeability criteria is nothing but you are allowing easy access of water to pass through. So that is the permeability criteria. So there are various criteria. Some of the criteria should be given here. The permeability filter should be high, right? So one is the retention criteria. This is given here to prevent piping. Another is the permeability criteria. Okay, now difference between aggregate filters and geosynthetic filters. So as I said, you can use aggregates, or you can use the soil, or you can use your geosynthetic. So how to use aggregate filters? You have to properly place graded aggregates in proper sizes like this. You have to place to form the filter, or you can directly use a geosynthetic. Okay, so these two options you have. Now what are the differences between these aggregate filters and conventional aggregate filters, and your this geosynthetic filters? Okay, so let us see. So what is the thickness of your conventional filter? It is very high. Okay, approximately this thickness is around 150 mm. Okay, around 150 mm. Okay, but geosynthetic, as you know, geosynthetic thickness is very low, only 3 to 10 mm generally. Okay, so you can see lot of thickness versus a very minimal thickness if you place a geosynthetic. Okay, then porosity, obviously geosynthetic you can have higher porosity. All right, higher porosity means you will allow more amount of water, higher permeability. Okay, now next you have tensile strength. Tensile strength, obviously aggregates do not have very tensile strength, but geosynthetics do have. Right, geosynthetic whatever you place, geotextile or whatever, geonet or whatever you place, geocomposite whatever you place, that will have some tensile strength. Okay, low to high, it can vary. But what you are using. Next, compressibility. Compressibility is very low in case of aggregates. Okay, the compressive, it is like compressibility means what? Tendency to of the thickness to decrease when you apply pressure. So that is very low. Okay, in normal cases it is very low, but in the case of geosynthetic, as it's very thin and it's like a textile, right? Textile or fabric. So if you if it's so the thickness is directly dependent on the normal pressure, okay, normal load on the that right. So that's why it is a function of the normal pressure. Means the compressibility is direct function of the normal pressure. Okay. Next, availability as per design. Okay, it depends on the query. Okay, query means from where you are taking the uh, aggregates. Okay, that is called the query. Okay, so it depends on the query, but for geosynthetic, it is manufactured under controlled conditions. Okay, so no problem with that. Capillary rise. So capillary rise, you know already what is capillary rise. So capillary rise is an important factor that you have to count in when designing with aggregate filters. Okay, but in case of geosynthetics, there is almost negligible uh, your capillary rise. Okay, then we have risk of damage. Risk of damage is there is no risk of damage in the case of your aggregate filter set. There is no risk of damage, but in case of geosynthetic damage, as you know, these are very thin fabric like structure, so while placing it should be very careful, because if you handle it very roughly, you might get say tears, you can tear, rupture, holes you can get. Okay, you can damage the geosynthetic. Okay, so you should be careful about it. Now these were the differences. Now uh, let us actually see what are the uh, similarities between the aggregate and geosynthetic. What are the similarities? Now the similarities are internal clogging by finer particles. So both of these filters can actually get clogged by these fine particles. Okay, these fine particles can easily clog the these geosynthetic filters. Okay, these fine particles can easily clog them. So that is one. Next is the biological clogging. So in what happens in warmer weather, where you have little warm weather, the microbes actually go and form colonies there. Okay, due to which what happens, these pores actually get clogged. Pores actually get clogged. So that is known as biological clogging. Clogging due to precipitation of salt. So what happens if there are if the salt content in the soil is high, then what happens, soils they precipitate into the filter and they actually clog the pores. Clogging in environmental applications, because due to various environmental effects they should might get clogged. And frost susceptibility, because of frosting during the winter season. This is mainly valid for very cold countries where we are designing. You should be very careful. Okay, cold weather where you are designing with the geosynthetics, for geosynthetics or whatever filter you are using, you should be very careful about that, because of this frosting, this freezing and all this, there will be you can damage the filters. Okay, you can damage the filter. Okay. Okay, so what we have next? Check. Yeah. What's happening? So, uh, yeah. So next we have some important property. So this figure you already have seen previously, right? The O90 size, O95 size. So you know already how to determine this O90 and O95 size using the sieve analysis. So if you recall, we use some glass beads to sieve and then find out the O90 and O95 size of a geotextile. So you already know that we studied in the first, second classes, right? Initial classes we studied about this, right? So this O90 and O95 sizes, these you should know for designing with any geotextile. Okay, you should know. So what is this O90 size? This O90 size is also called the aperture opening size, right? This is also called the aperture opening size. So this is very important. So this you should know, and this obviously all these things you can get using the sieve analysis. Okay, sieve analysis. So what is clogging? Filling up of the voids in the textile with solid particles progressively until the passage of water is slowed down. Okay, so what is clogging? So clogging means, as I said, what happens that you have placed one geotextile light for for the purpose of filtration. Now what happens slowly? The soil, very small soil particles, the fine soil particles progressively go enter into the pores and they clog the pores. They close the pores. Due to which what happens? Obviously, the water that was able to freely pass through the filter before is not able to pass now, right? The water passage becomes slow, the rate of water passage becomes slow. Yeah, so that is the detrimental effect of clogging. So clogging reduces the hydraulic conductivity, right? Now, what is internal clogging? Internal clogging happens by mineral particles, by precipitation and chemical deposition of particles from salt or related water, by biological growth, anaerobic conditions. These are the internal clogging. So, external clogging happens with the due to the effect of soil particles. The soil particles go, so fine soil particles go, stick into the uh, pores and they clog the pores. Okay, this is the external clogging. And internal clogging happens by the effect of this mineral particles, precipitation, chemical precipitation of salts, chemical deposition of particles from iron, lead, and water, biological growth, all those things. All those things come under the internal clogging. And external clogging is happens with the water, with the soil particles. Okay. There are various criteria. Okay, there are various criteria for deciding what should be the property of what filter you should use in what case. Okay, which your textile you should use in which condition. Okay, there are various criteria that is given that are given. Okay, so some of the criteria that are given here depending on the type of soil. So for granular soil you have one set of criteria, and then for uh, clay soil we have some other set of criteria. Okay, so there are two different sets, right? So for granular soil there are some set of criteria that is given. So one is the piping limit. Okay, O90 should be less than D80. So similarly for both granular and clay it is given. So what is piping limit? Piping limit actually arrests the piping. It does not allow the soil to pipe. Okay, pipe flow, that is it it is the what to say, retention criteria, right? Retention, that the soil is retained, it doesn't allow the water to pass. Okay, and then and the next criteria that you have to follow, always there you have to follow these two criteria. One will be the retention criteria, another would be the permeability criteria. So for adequate permeability of the soil, the adequate flow of water is there through the geotextile. So we have to follow this permeability limit. Okay, that is give it described for various different cases, and that is already shown there. Okay. Now there are some more criteria, that is permeability criteria, that are given here, the minimum water flow rate and all those stuff. So you can go through that. Okay. So these are some more guidelines. Okay, these are some more guidelines. So these are called the German guidelines, German guideline for filter. Okay, so here we have two types of soil. One is the stable soil and other is the unstable soil. So what are stable soils? Stable soils are those which have uniform gradation. Okay, uniform gradation or linearly graded broad gradation. Okay, well graded soil. So well graded soil, you already know. Okay, right. So how is the well graded curve? So like this, you have the grain size distribution curve. Okay, so all the soil particles, there is a equal distribution among all the soil particles. That's all the sizes of soil particles, there is a almost equal distribution. So that is the well graded soil. Those are the well graded soil, and uh, those are the stable soils. Okay, those are the stable soils. Now The other the thing that we have, that is the your unstable soils. What are unstable soils? So unstable soils are gap graded soils. Gap graded soil means the particles, these are not well graded. Rather, what happens is that in those soils, some sizes are completely missing. Okay, only some part sizes are present, some sizes are completely missing. So those are known as the unstable soils. So in unstable soils, what happens? There is a high tendency that the soil particles actually pass, enter. There is a high chances of internal movement of the soil particles. And what happens? These may then go and then clog. Either they may clog the filter, or they may start the piping phenomenon. Okay, they may start the piping phenomenon. Okay, so this we have, right? So stable soil, unstable soil. These are the two. Now, for stable soil and unstable soil, for both the soils, we have different geotextile criteria. Okay, and those are actually given by the German guidelines. Okay, German guidelines. Okay, so these are the some of the criteria, and this we using this, what we are going to do, we will solving one small problem next. Okay, small problem we will be solving. Okay. So in today's session, actually there is nothing much to discuss. Okay, these are very easy, and you will see that the problems also which we will be solving regarding filtration and whatever, uh, those are actually your this very easy, quite easy. Okay, they are quite easy, and easily will be able to understand also and solve. These are pretty straightforward and pretty easy. Okay, so we'll see them. Let's see this. Okay, for a particular soil, the D10 size is 0.3 mm, a D50 size is 0.07 mm, and the D60 size is 0.09 mm, and D90 size is 0.25 mm. Select a suitable geotextile for filtration by German method. So let us see. The first step that you have to do is you have to decide whether your soil is problem soil, or your soil is stable soil. So that you have to decide. Now what are the various criteria that is given here? The problem soil. So for problem soils, you can see it is written soil whose D50. So these are the properties of problem soils, right? The soil whose D50 lies between 0.02 and 0.10. Okay, so for soils whose D50 lies between 0.02 and 0.10, those are problem soil. Now for our case, what is the D50? It's 0.07. That means our soil is a problem soil. Like our soil is a problem soil. Now for problem soil, we have two criteria. This is one criteria and this is the other criteria. Now which criteria? Okay, so this is sorry, not this. Okay, which one should we use? Now we'll see our D40. Now D40. Uh, uh, can we see? Yeah, so D40 is greater than 0.06. D40 is greater than 0.06. So our D50 is given 0.07, right? D50 is given 0.07. So we can consider that our D40 will be greater than 0.06. 0.06 we can consider. So we can focus on this criterion. Okay, but D50 is greater than what? 0.07. So we can consider that our D40 is also greater than 0.06. Okay, D40 is greater than 0.06. Now we have this criteria. DW should be less than 5/10 of U. So first you have to find out DU. So what is U? U is nothing but the coefficient of uniformity, is nothing but d60 by 10 by 0.09 by 0.033. Okay, just 3, and U is less than 15. Why you are checking this criteria? Because you see here, soil with the reform coefficient less than 15. Okay, these are also problem soils. Okay, so again it is confirmed that our soil is a problem soil. Okay, problem soil. Now next, so we decided that we will be following this criteria. dw should be less than, dw is what? Dw is the apparent opening size. Okay, apparent opening size of the geotextile that you are going to use as a filter. Okay, dw should be less than 510, 5d10 u1 by 2, and your dw should be less than d90. So these are the two criteria. So dw should be less than 5 into 0.03 into 3 to the power 1 by 2. So which is should be less than 0.26, and this should be less than 0.25. So our dw of the soil should be less than 0.26, as well as you should be less than 0.25. dw of the geosynthetic, sorry, the dw, or the apparent opening size of the geosynthetic that you are going to use as a filter. Okay, the apparent opening size of the geosynthetic that you are going to use as a filter, dw, should be less than 0.26, and also it should be less than 0.25. So obviously, therefore, you should take a geosynthetic geotextile that will have a dw less than 0.25. Okay, so this is the final answer. You should choose a geosynthetic or geotextile that should have a dw less than 0.25. Okay. Now we have this gradient ratio test. The gradient ratio test we already just a second. Yeah. So this gradient ratio test, we already discussed in the previous classes, right? We already discussed in the previous classes, right? This gradient ratio. So what is this gradient ratio test? This gradient ratio test is actually used to understand the compatibility between the soil and the geotextile that you are going to. So to check if these are actually compatible. Okay, so with good compatibility the between the soil and a geotextile, what should you should ensure that the gr value, that the gradient ratio value, should be always be less than 3. Okay, should always be less than 3. Now how to find that gradient ratio we already discussed in the previous class, and now again here you can see that it is written, right? How to get the gradient ratio. So gradient ratio, so for all this, so before you implement, okay, before you before you implement a design in a site, okay, wherever you are going to use this geotextile filter, you should do this test. Okay, you should do this test, that you should check whether your the soil which is there present in the site and your the geotextile that you are planning to use as a filter, both of them are compatible or not. Okay, whether the site soil and the geotextile that you are planning to use as a filter, those both of them are compatible or not, so that you should actually ensure that you should actually check. So how can we actually check the compatibility? This compatibility, as I said, can be checked by this gradient ratio test. This gradient ratio test you have already, you can refer, so we already discussed this before only, so we won't uh, be going through that again, but slightly this is a very simple test where just to measure the heads at various points and then take out the ratio. And also if you see this graph, you can see that initially there is some hiccups, but later as time goes by, a steady state flow is established. Okay, the gradient ratio value actually stabilizes, but it is a stable state. Okay, and also if you see in these graphs, you can see what happens. So one, it is the system permeability, the permeability of the system, and below the graph which is shown, it is the weight of the soil piped. So as soon as the flow starts, a huge amount of soil, a large amount of soil will actually come out through the pores. Okay, initially to up to some time it will come out, but then as time goes by, you can see that this weight of soil the piped particles of soil, that is the soil particles that are coming out through the filter, that is reduced to zero. Okay, that is reduced to zero. That means what? That means the equilibrium has been established between the soil and the geotextile filter that you used. Okay, so that is good, right? Similar to the permeability, you can see it is reducing a bit at the start, from maximum value to start to reduce, because water soil that it is rearranging, it is going clogging, some adjustment is going on, readjustment between the soil particles and the geotexture is going on. But as time passes, you can see the system permeability also becomes stabilized. Okay, it becomes a constant value. Okay, so that means a stable state equilibrium condition has been achieved, and you should ensure that the weight of soil pipe becomes zero, and the system permeability, the stable system permeability is always greater than the required permeability, that you, at least minimum permeability that you want there. Okay, that you want to have. Okay. Yeah, now we will solve this problem. So before I solve, you just read the question once. You just read this question once and see if you understand the problem. Okay, see if you understand the problem. I will just give you 1 minute. You just read this question once and see if you are able to understand. We just go through this question once and then I will solve it for you. Okay, just go through and try to understand what is given here. So here we have a Gabian wall. Okay, Gabian wall, Gabian you should know now by now, right? What is a Gabian, you already know. Okay, you have steel meshes, steel nets within which you fill the aggregates and you form certain blocks. Okay, baskets of steel mesh within which you put the aggregates, and that actually forms the Gabian, and with that you have constructed a wall. Okay, that is the situation here, and there you are actually using a geotextile as a filter. Okay, now you have to choose, you have three candidate geotextiles, and within that you have to say that which geotextile you should use for your design. Okay, just read the question once and I will solve it for you. So what do we have? What do we have in the question? Given a 3.5 meter high Gabion wall consisting of three 1 by 1 into 3 meter long baskets sitting on a 0.5 times 2 times 3 meter long mattress as shown. Okay, so this is 2, this this direction it's 2, then this height is 0.5, and the other direction, this out of plane direction, you have 3 meters. Okay, similarly, these baskets are square baskets, one by one, and the out of plane direction, out of the this screen, this direction, that is 3 meter long. Okay, the backfill soil is a medium dense silty sand. Silty sand is there of D10 size 0.03 mm. Coefficient of uniformity 2.5. D85 is 0.15 mm. K is the coefficient of permeability of the soil, that is 0.0075 meter per second, and the relative density is 70%. Okay. Check the adequacy of three candidate geotextile whose laboratory test properties are given below. Use a cumulative reduction factor of 15 in order to adjust the ultimate laboratory obtained permittivity value to an allowable field oriented value. Okay, so yeah, so that cumulative reduction factor is given, which we have to divide by the this given permittivity values to get the design value. Okay, so we will see that. So final, what you would do, you decide that which geotextile we can use. Okay, which geotextile we can use for this purpose. So let us start. So first, what we will do, the first step in these kinds of problems is to calculate the permittivity or the transmissivity. Transmissivity in case of drainage problems and permittivity in case of filter problems. Okay, let us see how to do. First we have so what is the flow? Flow can be kh number of flow lines by number of equipotential drops, right? So here we have a flow net that is drawn here. So what, how many number of flow channels are there? 1, 2, 3 and 4. Okay, 1, 2, 3 and 4. How many number of drops? 1, 2, 3, 4, 5. 5 number of drops are there, and 4 number of channels. So number we can write kh nf by nd. Right, so 0.0075 is the permeability that is given to us. Then if h is nothing but the total head loss. Okay, so water from here to your height is 3.5, so total height we are taking the total water, this head into 4 by 5. Okay, now next we have to calculate the required permittivity psi. So Q is equal to KIA, you already know. K, what is I? I is del H by flow is occurring about the thickness by A. So phi is what? Phi is nothing but K by T. It is nothing but Q by A. So what is Q? Already found out. It is delta height 3.5 meters. And what is the area? What is the area about which the flow is happening? So wall is like this, right? Straight wall. Flow is occurred across this area. This is what, 3.5, out of plane direction 3 meter, so 3 meter, and height 1 meter. Sorry, what am I saying? uh, uh, yeah, total height is 3.5 meter, 3.5 meter, and times 1 meter, right? So total your uh, area of flow is that much, right? So find this out. this one I have a little bit confusion. This maybe this should be 3 meter. Okay, so please check once in the book. Okay, corners book, please check this one. Okay, this I think maybe this might be 3 meter. If one times 3 meter is the this given thickness, I think, I don't know, I'm not sure. Just check this once. Okay, maybe this one should be 3. Just check once. Okay, just check in book. Okay. Okay, now next you have to find the allowable permittivity or a design permittivity. What is the design permittivity? Is the ultimate permittivity divided by how much? All the reduction factors: reduction factor due to soil clogging, binding, reduction factor due to creep, then reduction factor due to intrusion. Okay, then reduction factor due to chemical clogging, then reduction factor due to biological clogging, and all those things. So cumulatively it is given that all the reduction factors, if you combine the in the question, you can see it's given as 15, given as 15 by 15. Now for all the geotextile we will write it. Okay, geotextile 1, geotextile 2, and we have geotextile 3. Okay, geotextile 1, geotextile 2, and geotextile 3. For geotextile 1, the ultimate is 2. So what is the uh, allowable? 2 by 15. 2 by 15, how much is 2 by 15? 0.13. Then for geotextile 2 we have 1.2. So we have 1.2, then 1.2 divided by 15, we have 0.08, and for geotextile 3 we have 0.4, so we have 0.027. Right, now next what do you have to find? You have to find the factor of safety. Now what is the factor of safety? Factor of safety is the allowable by psi required. So what is the required psi? The required size this much, 1.71 to the power minus 3. So this allowable, these are the allowable values, 0.13, this is. So for all this, if we do this, we will get a 76, 47, and this one will be 16. So all are acceptable. Okay, so all are acceptable. So all the geosynthetic geotextile candidates, all of the geotextile candidates, all of them are equally good for the permeability criteria. Okay, all of them satisfy the permeability criteria very nicely. Okay, all of them satisfy the permeability criteria very nicely. Okay, so next we have to check one more criteria. So permeability criteria, if we satisfy, the other criteria also have to check. So other criteria that we have to satisfy, that is the retention criteria. So as I said, there are various retention criteria that is given by many researchers and many people. So one of those criteria is Carroll's criteria. So Carroll's criterion says this O95 should be less than 2.5 D85, and your O95 should be, that is O95 should be, what is D85? What is D85? D85 is given, right? D85 of our soil is 0.15. So it should be less than 0.375. That is the O95 should be less than the uh, 0.375 mm. Okay, this is aperture opening size should be less than 0.375 mm. Okay, now let us see what aperture opening size you have: 0.3, 0.42, 0.21. So this is fine, this is fine, right? So candidate geotextile 1 and 3 both are acceptable. Okay, both are acceptable. Now this is one more problem which is similar problem. Okay, so try to see if you are able to solve this one. Try to read the question once and see if you are able to understand. Okay, so yeah. So design a geotextile filter surrounding an open graded stone aggregate that in turn surrounds a perforated pipe under drain as shown in the sketch below. So we have a stone pavement here, so water will come from the pavement to the stone base, then the soil subgrade, then water should enter. So we want the water should come and enter into the drain. This drain is there, like this is drain is there, pipe like this come into the drain. So that the water enters the perforated drain, we have placed some crushed stone. Around the crushed stone we have placed a geotextile as a filter, so the only water passes into the drain but not the soil. The soil should not enter. Okay, only the water should enter. So this we have actually one. So flow will enter through the stone base from the upper part of the under drain, while soil infiltration will come from the surrounding native soil. As I said, the soil is a dense silty, so water will come like this. Okay, right? So what from here water, so from this is a pavement, so pavements, if rain is here then water will come like this into the shoulders, right? From here it will enter, it will come here. Okay, and it will also come like this, and there are chances the soil might enter from here, right? There are chances. Okay, The soil density is a silty sand with the relative 11 properties 15% non-plastic fines with CC 2 Cu5 RD is given. RD is nothing but the relative density 80% D50 size is given. Coefficient of permeability is given. Geotextile being considered is a non-woven needle punched. Non-woven, so already you know what is not a non-woven needle punched geotextiles, and the permittivity values are 1.5 second inverse and apparent opening size is 0.212. So there is the O95 size is given as 0.212. O90, sorry, O90 size is given as 0.212. So let us start. So the approach is quite similar. Okay, whatever approach we used in the previous problem, the approach will be same. The how you need to proceed the problem, that will be same. So first you need to assume the flow. For in this case, how to calculate the flow of water that is coming. So that we need to assume. Okay, how much infiltration happens in some area. You have that type of hydrological data. You can get how much water will actually inflow. Okay, that you can get from the hydrological data of that place, of that city or that part. Consideration the part. Okay, now flow. Area. Now what is the area flow? uh, so this head is taken as 450 mm. Okay, so this is the head that is taken. Okay, and what is the this one? So it is said that water. Okay, now see here, while soil the water for the flow through the stone is upper part of the under drain. Okay, so water flow is from the upper part, this part. So this is 300 mm, right? So 0.3. This one if we will do, it will come out as second inverse. Okay, pay proper attention to the units. Okay, pay proper attention to the units. Now I have to find out the allowable. Okay, the allowable is given by, as I said, so if you see corners book, you will see that all these factors are defined and the standard values are also given. Okay, for various uses these are given. So I am just taking the standard values for this case. Okay. Factor of safety for flow criteria is acceptable. Okay, it is fine. It is fine for us. Now next is the retention criteria. As we said, for retention criteria there are a huge number of criteria that is available. So this is one chart that you can follow. This is after Littich et al. So you can actually follow this chart. So in our case what we can do, what is the, let us check once. Okay, let us check what is the cc value. Cc is 2. Okay, cc is 2, cu is 5. Now let us see here. So from the less than 10% fines and less than 90% gravel, D10 size is greater than 0.075. D10 is it given? 4.8. So return size is not given, but 15%. So you can take this one. Okay, this criteria you can check. And then what we can do, our cc is 2, cu is 5. Okay, cc is 2, cc is between this, right, 1 and 3. So from here then cu is 5. Okay, relative density is how much? Relative density is 80%. cu is 5. Okay, so we'll take for this, then relative density is 80%, so greater than 80%. This criteria. Okay, this criteria you can take. O95 should be less than this one. This criteria, okay, O95 should be less than 18 by cu d50. Okay, so let us write that. So properly see the chart and you can choose. O95 is required is less than 18 by cu d50. So 18, what is the cu5, and d50 is also given, be less than 0.126 O95 required. So what is the O95 of the geotextile that you are using? The geotextile has a O90 of 0.212. Okay, so 0.212 is obviously not less than this. So 0.212 is not less than 6. Thus we can write the current geotextile in a consideration can't be used in the present scenario. Okay, hence we cannot use this. Okay, quite simple, just you have to directly follow the given criterion. Clear, right? Are you able to understand or not? Tell me. Very simple, extremely simple problems. Okay, don't have to use too much brain. Very simple. Okay, problems are very extremely simple and straightforward. Okay, I hope you are able to understand. Just a sec. Let me check the next problem. Just a second. Mm, yeah. Okay, so this was the end of drainage. Okay, drainage. Now next, what we will see your the other counterpart of filter, that is the drainage. Okay, filter we already saw. This was the filter, and now we'll see the drainage function. Okay, drainage function. Let's see. So what is drainage? Before what? So drainage is, the filter was what? The main purpose of filter was to prevent the passage of water, of the soil, and the allow easy access of water through it. Now the purpose is almost same, just a different side of it. The main purpose is to allow water through, carry water through it. The main purpose of the geosynthetic is to carry water through it and uh, drain it out. Okay, the main purpose is to carry your water through it. Now you should be able to carry large amount of water through it. You see that I'm saying through it means inside it. So water should flow within the geo textile or whatever the geosynthetic, and it should finally drain out. Okay, so that is one. Okay, so as I said, what we can do, so say you have a pavement like this. Okay, you have a pavement, or you have a pavement, and below, what we can do in the subgrade, you can put a geotextile. So what will happen, as it is raining, water will enter into the pavement, percolate inside to the geotextile, and then the water will pass through the geotextile. The geotextile is going to carry the water through it, and then finally drain it out into the drains, that is here, is there. Okay, so this is the main purpose of the geotextile here. Here the main purpose is to carry the water through it and drain it out. Okay, now what are the drainage applications? Pavement edge drains, as we saw already, pavement edge drains. Then interceptor trenches on slopes. Okay, interceptor trenches on slopes. So we have a slope. So what we do, at the base of the slope we put some trench. Okay, interceptor trench. What happens? The water will come and then come and then drainage into the trench. Okay, drainage and abutments and retaining structure. So this we already discussed in the initial classes, right? Initial classes, when we were discussing the functions of geosynthetic, at that time we discussed this, isn't it? So what is this drainage function behind retaining walls? Okay, why is it very important? All those things we discussed, right? So behind the face of the retaining wall, we have to provide adequate drainage of water. Then relief of water pressure on buried structures, substitute for conventional drains, leachate collection and gas venting. So this you don't know till now, so we'll discuss it later also. So what is leachate collection and gas venting? Means when you, so you know about landfills, right? So landfills what? So landfills, here you dump all your garbage. Okay, so what do you think, what happens that the municipal truck comes every day and takes your garbage from your home and it dumps somewhere, right? It processes it and it dumps it somewhere. So most of these are dumped in these landfills. Okay, landfills. So in the land there is a trench made, and inside the trench you dump the waste. And these are actually engineered landfills. There are engineered, non-engineered landfills, both are there. Previously, many years, 50, 100 years back, most were non-engineered landfills, but nowadays, in the last 100 years, 50 years, most of the landfills are engineered landfills. That means you have a lining here that is made up of geosynthetic clay liner, or say geomembranes. Okay, those linings are there, and those linings actually prevent the passage of these harmful chemicals, or some chemical action will be there, right? Speed decomposition and whatever. So it does not allow that to come out of here. Okay, now even if some amount is coming here, so what we can do, we can provide some drainage layer here. Okay, drainage geosynthetic. So what happens if it comes, whatever leachate is coming, it can come and it can come out of the this, you can have some drains here, it can come to the pass through the geotextile and come to the drains. Okay, that we can do. That is one thing is that these are generally covered. One is the covered landfills. Okay, covered landfills. What happens, these landfills are covered. So due to the biological processes, what happens, due to the action of microbes, the gases such as methane and all are formed here, or these gases are formed here. So it's our responsibility to drain out the gases also. Else what will happen, else there are chances that this landfill might catch fire and all those things. Okay, so it's our target that we should drain out the vent out this. Yeah, so for that purpose also we can use some geotextile here. Okay, so a certain amount of geo synthetic, which can actually carry the gas through it and then finally vent out. Okay, then finally vent out. Yes, that also we can do with the help of this. Drainage mats in horizontal applications such as roofing. Okay, these are self-explanatory. PVDs for accelerated consolidation. So you already know, in the previous class we discussed PVDs in details, right? So how PVDs help in accelerating the consolidation process by reducing the drainage path by allowing more drainage. Okay, so that we already discussed. So these are various types of core that edge are drainage. So you know about geocomposites, right? We studied about geocomposites, where you have two geotextiles that are placed top, the top and the bottom. Those work as the filter. In the bottom you have a geonet. In the middle we have a geonet. Okay, so you have, say, one geotextile placed here, then we have one geonet placed, one we have a geotextile placed here. The geotextile that are placed, this geotextile placed at the top and the bottom, this geotextile actually serve as a filter, and the here the geonet that you place, this actually serve the purpose of what, a drainage layer. Okay, because since you know geonets are nets which have like 3D surfaces, and they can actually easily allow water to pass through it. So this is the core, and there we can have various cores. Okay, various cores. So one, we can have stiff 3D webs or mats, then we have extruded set of intersecting images, that is the geonet that we use. Okay, then you can have single and double cuspated sheets, then we can have deformed sheets, where these types are generally used in your PVDs. Okay, or in three-dimensional boxes and trusses and that also. Various types of cores you can have, which actually aid in drainage, which allow large amount of water to pass through them, or carry to, they actually aid in the carriage of water through them. Surrounding the core we have a geotextile as a filter. So as I said already, surrounding that core we have a geotextile layer that acts as a filter. Now here in this case drainage is nothing but the in-plane drainage, right? So say you have the geotextile, this is the geotextile. So in the plane of the geotextile, this flow is happening. Okay, plane of the geosynthetic. So this is the in-plane drainage, it's an in-plane flow. In that case, this in-plane flow of the flow capacity is defined in terms of the what? Defined in terms of this transmissivity theta. Transmissivity theta is nothing, can be easily determined with the help of some various tests such as the constant head test, where you maintain a constant head between you have the geo textile and the composite that is carrying that you are going to use a filter, and then you maintain the head and you measure the flow that is happening in some amount of time. So you get the total volume of water that is flowing, then you divide by time, you get the flow. And you know the already know the area of flow, area is happening through what, this width times the thickness. Okay, this is the area of the flow that you already know. Then you have the I, that is hydraulic conductivity. This is nothing but the head of flow divided by the length of flow, that is that you already know. From all these things what you can do, you can determine this theta. This theta is nothing but kp into t. Kp is the in-plane permeability coefficient, T is the thickness, and theta is known as the transmissivity. Okay, theta is known as the transmissivity. Okay, so yeah. So as I said, there are various these reduction factors that we studied, right? So various reduction factors, those are some of them are given in Corner's book, and that table I've actually given here. So for various applications, we have a very different range of these reduction factors. Okay, so that you can easily refer from here. You can easily take from here. Okay, you can easily choose from this table. Okay. So some more. So here we have the value for allowable flow rate. To get the allowable flow rate, we have the allowable for transmissivity of, for this is for geotextile. Okay, and this is for geonets. Okay. Okay. Okay, so we are almost nearing the end of today's session. We don't have too much to discuss today. Let me just check once. Yeah, so we have, yeah, we don't have too much. So let us see this problem. Let us see this problem. A 10-meter, okay, yeah. So here is the problem. Yeah, here is the problem. Just read the question once. A 10-meter high zoned earth dam is to be used as an irrigation reservoir with the cross section as shown. So the cross section of this irrigation reservoir is shown. Okay, the cross section of the irrigation reservoir is shown. A geotextile is being considered behind the clay core wall. So this is the clay core wall. So this is the zoned earth dam, and we have the clay core, right? So in the clay core wall, here we are planning to have a geotextile drain. So that water that comes here can easily flow out like this, okay, into the final drain, toe drain. Okay, so we are planning to have this. A geotextile is being considered behind the clay core as a chimney drain and the drainage gallery. The geotextile under consideration is a 2000 gram per meter square. This is the what weight of the geotextile. Okay, weight 2000 gram per meter square non-woven needle punch geotextile with ultimate transmissivity of 15 into 10 to the power minus 4 meter square per minute. Use a cumulative reduction factor of 3 is given to us. Cumulative reduction factor is given to us directly so that we do not have any confusion. What factor of safety does this geotextile have for the amount of flow seeping through the clay core wall, which is a clay silt of permeability 10 to the power minus 7 meter per second. So the permeability of the clay core wall is given, and yeah, permeability of the clay core wall is given, and what? Uh, yeah, and the transmissivity is given, fluid reduction voltage. So it's quite easy and straightforward. We'll let us start. Yeah. So what is the first step? What is the first step that we need to follow? In all the problems, what is the first thing that we need to follow? Please try to answer. You should be able to answer this. What is the first step? What is the first thing that we need to follow in this kind of problems? In flow, in your drainage and filtration problems. What is the first thing that we need to do? Now you can write in the chat box also, right? Please type it. What is the first thing? First thing is you need to calculate the flow, right? We need to calculate the flow. The calculating the flow is the first step that we need to follow. Okay. E is equal to, so you have to use the flow nets, and this is given. What is the height of flow? This 10 meter. Yeah, this 10 meter. And what is the n number of flow channels? 1 2 3 4 5, 2 3 4 5, and drops are 2 drops, right? 1 2. Nothing but 1.9. What is the gradient of flow? Gradient of flow is sine. So flow is according across this path, right? So sine of 75 will give us the this one, right? We take like this, take 75 sine. Take this by this. Speed, then next C you can have what, 0. How much? Sine 75 is how much? Sine 75. Next again, Q is equal to KIA. KIA is thickness times width. So Q is equal to KTI into omega width. So uh, theta required is equal to KT is equal to Q by pi equal to 1.5 into okay, fine. Next we have factor of safety now by theta required, right? Theta ultimate divided by cumulative reduction factor by what is 3.22. So this is quite low factor of safety. Okay, so generally what we do, generally we require factor of safety 5 to 10 generally. Okay, so okay, so after this do the soil retention analysis using various criteria that we already discussed. This one as shown previously. Okay, now next similar problem. So we have a cantilever retaining wall. Behind the retaining wall we have put a non-open geotextile. This non-open geotextile will actually carry the water through it and actually drain out through this peephole. Okay, so we have an 8-meter high concrete cantilever retaining wall. It has an allowable transmissivity of 0.15 into the power minus 3 meters square per minute. And the soil backfill is a silty sand with K is given. Okay, so quite simple again. First again what we will do, we'll remind the flow. So how many flow channels? 1 2 3 4 5. How many drops? 1 2 3 4 5. 5 by 5, times 60 for the unit conversion per minute. Okay, please pay attention to the units. Okay, very, if you make mistakes in the units, your whole problem is going to be wrong. Okay, is 1. Okay, flow is going straight along this line. Same, okay, same, similar to what we did the previous problem. Okay, so which is not nearly acceptable, very less. Okay, so we need to use some mode. Any other geosynthetic? Okay, any other property of geosynthetic? Okay, we have to change this geosynthetic. We need to use some other. Okay, let us see this. A refrigerated storage building for frozen foods is to be founded on a side illustrated below. A capillary break beneath the building's foundation having a geotextile is being considered as a solution with a 700 gram per meter square non-wind pump geotextile having a liable transmissivity of 0.0007 meter square per minute at 25 kp normal stress. Be adequate if they required. Okay, we have to check if this geotextile is adequate for the given condition given the factor of safety, minimum factor of safety that you need to have, that is 3. Given upward flow rate of water is 2.7 10 to the minus 6. So what happens? So there is a tendency of capillary rise in the soil. Okay, the upward flow of water is due to the capillarity. Water is rising above, rising from bottom to top at the rate of 2.7 into 10 to the power minus 5 meter square per minute. So for that, what happens if you do not provide this capillary break in between? What will happen? The water will come here, and then this is a frozen food building, right? So this is very cold place. So this water might actually get frozen near to the building. Then again it will, okay, it might get frozen. And if water gets frozen, you know that it's water. What if water freezes? You know that it's going to expand, and this expansion of water is going to actually result in some problems, such as it may create cracks in the building and all those stuff. Okay, so due to this, what we need to do, we need to prevent the water from going up and reaching the building near the building foundation or the building base. We need to prevent that. For that, we have provided a capillary break. And what is this capillary break? So what we do, we provide a geosynthetic filter, a geosynthetic drain between. So what happens, the water comes, enters the drain, and then finally drains out through the this pipe drains, that is there under drains that are there at the sites. Okay, comes, water comes and then flows along this path, and then finally drains in the under drain. Okay, the slope of the this geotextile that you have to lay, it's given as 5%. Okay, the camber that you have to maintain for this geotextile or geosynthetic for this drain, it's given as 5%. Okay, so just we have to check whether the given candidate geotextile is fine for this purpose or not. First, again the flow. So P, the slope is given. Next, Q, transmissivity you have to find out. Okay, factor of safety, allowable theta required. Theta allowable, what is the theta allowable? It's given allowable transmissivity of 0.0007. It's given, right? And required it's 5.4 into 10 to the minus 4. This comes out as 1.3, which is less than the required factor of safety of 3. Okay, hence not acceptable. Hence this candidate geosynthetic is not acceptable. Need to change it. Change it. Okay. Need to change that. Okay. And so now we have this last problem that we need to solve. It's also quite similar and straightforward. So let us see the problem. Okay, this is also quite similar and straightforward problem. Design the drainage factor of safety for the geonet behind the 8-meter high cantilever retaining wall. Again, your retaining wall as shown below. The response curve of the geonet is also shown below. So you know, as we know, right, it depends upon the flow rate. What the rate at which the water is going to flow through the geonet or geotextile, that depends on the vertical pressure on the that geosynthetic, right? The vertical pressure, if the pressure is high, then obviously the flow rate is going to be low, and if the pressure is less, the flow rate is going to be high. So the response curve of that particular geonet for the flow rate versus the normal stress for various gradient of flow is given here. Okay, the soil backfill is a silty sand with a permeability coefficient of 500 to the power minus 5 meter per second. Now we have to check this thing. Okay. So again the same will be initially what same first step as usual, we have to determine the flow. So k h n f by n d, what is the number of flow lines? 1 2 3 4 5 1 2 3 4 5 5 closed channels and 5 drops, right? 1 2 3 4 5, we can consider 5. 1 2 3 4 5, okay, and 1 2 3 4 5 channels you can consider. Okay, so let us do this. Sorry, so to come out test 4. Is the gradient sin 90 this one. What is the average normal stress? You can take half times 8 into 18. Okay, assuming 72 kPa. Now from the given response curve, zero and normal stress 72 kPa, we get, so approximately from this response curve for I and for us it's 72, right? So it will be something here, something around in this region. So it will be approximately. So take proper scale and find it out. The ultimate is equal to, see the book, okay, properly the graph is given there. So please refer the corners book. 10.6 into 10 minus 4 per second, which is again equal to 1.56 into 10 minus 3 per second. theta allowable, okay, but theta ultimate by reduction factors. So reduction factor, it's not given here, right? So it's not given here, so approximately from the tables which I had given you, from there you can take the approximate reduction factors as 2.62 total, multiply and take 0.595 into 10 to the power minus 3 meters per second. Therefore factor of safety is q allowable by q required 3 by how much? uh, 4.4 into 10 to the power minus 4 means 0.4 into 10 to the power minus 3. So this will come out as 1.48. So this is not actually marginally acceptable. Marginally acceptable, not at all acceptable. Okay. Right. So this was all for today's session. So with this we will end today's session, and this was the last problem for today. And I hope that everything, it was very simple, okay, nothing much to discuss. It was extremely simple session, and next two sessions are also going to be very straightforward and very simple, and the last one session we will just wrap it up. Okay, everything. So I hope that you understood all the concepts very nicely and properly, and you are able to follow the steps and follow everything. And if you have any doubt, please feel free to contact me anytime, write to me anytime. I will be more than happy to help you. Alright, and please prepare well for your exam, prepare all the concepts, solve all the problems, design problem, everything solve properly, everything the way it is done in the main theory classes by Professor K. Rajagopal. So everything the way he has solved, try to solve everything that way, try to practice all the problems, and definitely I am hopeful that your exam you will perform very well in your exams. Okay, and yeah, so with this we will end today's session, and before we end I will just mention you about the next class. So the next class will be on next Sunday, right? So next Sunday is when? Next Sunday is 6th, right? Next Sunday is 6th of October, uh, right? So next class, or next session is better term, right? Not a class actually. Next session will be on 6th October, Sunday, 3 p.m. to 5 p.m. Okay, 6th October, Sunday from 3 p.m. to 5 p.m. Alright, so with this we will end today's session. Thank you so much for attending, and you may leave now. Okay, you can leave the meeting. Okay? Alright.